And this does automatically start recording, by the way.
Okay, sounds good. Try not to say anything that, is controversial.
Sure.
Although research is always controversial, so
That's right. We have to have some freedom of thought.
Yeah. You want more views and more clicks.
Yeah. Well, I'm not getting the the revenue from YouTube, so yeah, maybe for my own channel. So this is a required colloquia for like what's, or is it optional colloquia?
It's optional. It's a very pertinent question, actually, since that's one of the things that we've been discussing internally, whether or not to change the format and integrate it into the curriculum. But it is at the moment just an open colloquia that happens on a regular basis.
Okay, wonderful.
Mm-hmm.
Cool.
Yeah. So we'll welcome everyone who's been joining in. I guess we'll wait another minute or so. We've got a pretty decent crowd going already, but we'll wait shortly to begin.
Sure.
Okay, I think we've hit a pretty good baseline. So let's launch into it then. So thank you once again to everyone for joining us today, this morning. We're very happy to welcome Professor Waheed Bajwa here, who will be talking to us about high-dimensional regression and dictionary learning, some recent advances for tensor data. Professor Bajwa is from the Department of Electrical and Computer Engineering at Rutgers University in New Brunswick, New Jersey. And his research interests include statistical signal processing, high-dimensional statistics, machine learning, inverse problems, and network systems. And he is an associate professor at Rutgers, as I mentioned earlier. He's received a number of awards, including the U.S. Army Research Office Young Investigator Award, the NSF Career Award, and the Rutgers University Presidential Merit Award, awards and recognition for teaching excellence as well. So a number of recognitions that I think will demonstrate, how interesting the talk will be today. And we're glad to see a good audience. I think it reflects the interest of the department as well in this topical area. So we've already asked our speaker about questions and his preference for how to handle them, and he's told us that he's happy to address questions as we go. So please feel free to use the Q&A function that is available here, and we'll keep an eye on it. And if anything comes up, we'll relay the questions to our speaker and get them addressed. And we'll also, I think, leave a little bit of time at the end for questions to go through those as well. So with that, Professor Bajwa, please feel free to take it away. Thank you very much.
Thank you so much, Sparse, for the kind introduction. Thank you to both you and Michael for inviting me here. It's a pleasure to be here again. I was virtually. I visited NCSU in person quite a few years back. I think like 5 or something. So unfortunately, I can't be there in person, but happy to be here virtually. So as was mentioned, I would love to basically entertain questions as we go along so that we are all on the same page. I really believe in the idea that it's better to cover less but cover that well rather than cover a lot and not really leave a lot of audience behind. So with that, let me get started. I do want to acknowledge that this research is supported by the National Science Foundation and the Army Research Office through a grant that completed a few months ago. So let's jump right into the problem and also give a shout out to my collaborators, my former students who now have all graduated. The talk has two parts. The first part will involve work by my former PhD student, Talal Ahmed. The second part involves work that, from my PhD student, Zahra Shakiri, Mohsen, and my collaborator, Anand Sarwate, and Mohsen Ghasemi. And Harun Raja also contributed to the first part of the talk. So with that, let's get started. I've tried to divide the talk into three major pieces. The first one is the motivation for what I mean by tensor data and why do we, what tools do we need to bring to the table to deal with that tensor data. The second part then specifically focuses on the problem of regression when we have tensor data. And then the third problem deals with the problem of feature learning, which we do using dictionary learning method. I'm being ambitious here and I have included both these things. My feeling is I may not get to cover the dictionary learning that much, but we'll really try to go as far as we can. Okay. So let's get started with the motivation. For people who are in statistics or statistical signal processing, or signal or other related areas. Just a reminder that one of the key tools that we use to solve many of our problems in machine learning, statistics, signal processing is the idea that our data lies is around some low dimensional structure, geometric structure. Now, classically, when we solved signal processing, machine learning, statistics problems, it ended up that the data itself was low dimensional. And what I mean by low dimensional, let's classify that. It's a relative term. A relative term in the sense that low dimensional is defined by the aspect that the number of data samples that you have to solve a given problem exceeds the number of features in each sample. So for example, if you take the classical statistics iris data set, right? It has three features and you have a bunch of data samples. So in general, what we have is, for example, we have social sciences, medical sciences, paleontology. In the past, we had a few samples. For example, you had a certain number of, let's say, features that you were looking at within medical sciences. You didn't have access to gene data, for example. And the number of samples far exceeds the number of features or attributes. And so what you would do, for example, let's take the example of linear regression, and I'm going to use here mostly the language of statistics, but so don't get confused by that. So in the language of statistics, we have basically what we call a response variable, or you can call it signal Y. And then we have P covariates or predictors, which are basically attributes. Think of them as attributes. And low dimensionality is defined by the fact that N, the number of samples, which is the dimension of your signal or response variable Y, exceeds the number of your predictors, P. Okay, so for linear regression problems, you can write the problem the classical way: Y equal to a matrix times the vector. X is your matrix of what's called predictors. Beta is your unknown parameters plus some noise. Your goal is to recover this unknown vector beta, okay? And this matrix X is a tall matrix and it is not very wide. So tall in the sense that N is much bigger and the width is corresponding to the number of predictors that you have. So you have an overdetermined system of equations and you can solve it very easily. So what are the advantages of low dimensional? Again, the whole aspect of low is relative, n is greater than p. Just remember that, right? Number of observations is greater than p, the number of unknowns that you have in the system. The advantages are you have less fear of overfitting, memory requirements are low, computation can be easier. Now, what's happening as we move towards the modern data-driven world is that we have cheap sensors, abundant storage, digitization, and now we are in the high-dimensional setting. And the high-dimensional setting means that the data dimension, the number of features or independent variables or predictors or the unknowns that we are trying to determine, right? That far exceeds the number of samples that we have access to. And the examples are again from the same fields, except that now we have more tools. So let's focus again on the problem of medical sciences. Now you may have 500 or 1,000 patients, but with each patient you can do, for example, you can do their genome-wide study, and you have now thousands of genes, and you are trying to figure out something about what is going on in the body. Now you have tens of thousands of unknowns and maybe 500,000, 1,500 samples. So we are now in this high dimensional setting, which is defined by the observations n is smaller than the number of unknowns p, right? Now, what's the issue with high dimensional setting? If you, for example, go back to the linear regression problem, we are in this now underdetermined setting. We have a less number of equations and more unknowns. And classical linear algebra, of course, tells us, well, that's going to be a challenging problem, right? More unknowns, less number of equations, you are not going to be able to get a unique or correct solution. So the challenge with high dimensional data is that you have overfitting is a real concern, more unknowns than number of equations or observations. You also have large computational and memory overhead that you have to deal with. And so how do people solve this high dimensional problems? Well, the idea is that, well, even though the data is high dimensional, the key information is still contained in some intrinsic low dimensional structure that you can exploit through an appropriate regularizer. So the classical regularizer that most people are familiar with in the area that we work with is sparsity-based regularizer. So you have this more more unknowns than the number of equations. How do you solve it? Well, you assume that some of the unknowns are zero. So that's called sparsity. So we assume sparsity-based regularizers, and that can be used to solve these high-dimensional problems where you can actually get the right solution even if the equations or the number of observations is smaller than the number of unknowns. So sparsity-based regularizers are commonly used in sparse regression, sparse approximation. The poster child of sparsity-based regularizers is compressed sensing, of course, and dictionary learning and so forth, okay? Then people realize that these sparsity-based regularizers typically apply to vector value data set, and then people also posed for matrix value data sets, also posed additional regularizer, which was based upon the idea of low rankness. So now you assume that the unknowns that you are dealing with has a matrix structure, so P1 by P2, but instead of the number of unknowns being P1 times P2, you assume that this matrix has a low dimensional representation in the sense that it has a low rank. So it is given by a product of two matrices U times V transpose, and each one of them has, so the rank of this is R, and R is much smaller than P1 and P2. So now the number of unknowns that you have is only R times P1 plus P2. So instead of P1 times P2, now you have P1 plus P2 times R unknowns. And by imposing this, you can still solve the problem. And this low rank regularizer is used in matrix regression, matrix completion, background suppression. PCA, of course, is based upon the idea of this low rankness and so forth. And one of the key themes that emerges from this low rankness or this other regularizers is the following: that even though you have less number of observations than the number of unknowns, the number of observations N as long as the number of observations n is on the order of the intrinsic dimensionality, the intrinsic number of degrees of freedom or unknowns, you can solve the problem. So for example, if you are doing sparse regression, you assume that the sparsity is S, which is much, much smaller than the number of actual number of unknowns is P, but only S of them are non-zero. So you really need to recover S. And so it turns out that you need the number of observations to be only order S times a log factor. So what you care about is really this S. And if S is much smaller, you recover the problem exactly. Similarly, for matrix regression, if you say that rank R is much, much smaller than P1 and P2 simultaneously, then the number of unknowns is P1 plus P2 times R, and the number of observations you need to solve this problem is order P1 plus P2 R times the log factor, even though the original unknown structure is P1, P2 dimensional. Okay, so you can see that there is huge savings when we impose these kinds of regularizers. Okay, so hopefully this is, the motivation is clearer. Now let's go to the idea of tensor data. So it turns out now that as we are again moving forward with our technology and the digital devices, now actually we can collect multi-dimensional data, or what's called multi-way data or tensor data. So now the data having 1 dimension or 2 dimensions, now you can have 3, 4, 5 dimensions. So for example, fMRI data, right? It has a spatial and it has depth. It's a 3-dimensional tensor. So you are observing a volume. If you have fMRI video data, that's a 4-dimensional tensor. So a colored image, for example, is also a 3-dimensional data, right? You have spatial X, Y, but then you have 3 color channels. So you are also looking at a 3D structure. So now we are increasingly being faced with the tensor data, but the kind of regularizer that we used in the past were designed for either vector or matrix value data. Now, it turns out that tensor data, just by the fact that it is 3D, right, or 4D or so forth, if we use the old regularizers, which we can apply here, that's not that we cannot apply them here, the requirement that we end up with on the number of observations is very suboptimal. So let's take a simple example. Let's say I have this fMRI image and the unknown is, I'm just giving a pictorial thing. And we have a tensor B, which is 256 by 256 by 64. So on an individual level, it's not a huge thing, but because it's 256 by 256 by 64, in 3 dimensions, it becomes huge. Now you say, well, I don't care that it's a tensor. I'm going to just do, like, for example, many people even do PCA today by take an image. For images, you take the image, you vectorize it, and then you do PCA on that, right? So you reduce it down. So you say like, oh, I don't care, it's a tensor. I'm going to vectorize it. I'm going to just maybe by any order, rows, columns, or going back and forth, raster scanning, I vectorize it. Well, sure, you can do that. If you do that, then it turns out that the vector dimension is about 4 million, okay? Now, people who work in kind of sparsity-based regularizers, a rule of thumb is like, okay, you know, if you assume about 10% sparsity, it tends to work pretty well. So you say, okay, I have a 4 million dimensional vector now, and I will assume that it has 10% sparsity. If you do that, then the requirement you end up getting is that you need the number of observations to be about 400,000. Now, remember that many of these problems are practical problems. And for example, if each observation, let's say the patient, so think back to some of the largest COVID vaccine trials, they have 70,000, 80,000 subjects in them. And we consider them really big trials, right? So here we are talking about 400,000 observations, or if you want to relate it to patients, if you want to apply the old regularizer of sparsity. So the message here is that if you want to deal with this we are already in the high dimensional setting, but if you want to deal with the tensor data, that basically just because of the fact that it is now multidimensional, the number of unknowns explodes. And if you try to apply the old regularizers, you will have quite a few challenges in solving the problem because the number of observations that you need explodes. And in many problems, that's not possible. So the whole idea behind this talk is that when you are dealing with tensor value data in high dimensional settings, what you should do is really exploit tools from tensor algebra to exploit the tensor geometry and impose regularizers that are based upon, for example, tensor decompositions. So there's a whole literature on tensor decompositions, and there are works that have applied this try to exploit the tensor geometry. Here are some reference works. These are all tutorial papers. In this talk, I'm going to talk about two things where they haven't been applied in a manner that is, I would say, satisfactory previously. One is for tensor regression. This is a work that appeared last year in Science Journal of Mathematics of Data Science. And the other is in dictionary learning, which is a collection of works that appeared. And also we have a book chapter that just came out from Cambridge University Press. So this concludes the first part of my talk, where we motivated what is the meaning of high dimensional data and why does tensor data require new set of regularizers. I'm now going to jump into the problem of high dimensional tensor regression, which makes these ideas more concrete, but this may be a good time if there are questions to address them. If not, I'll keep going.
No questions have come in yet, but to the audience, please feel free to enter any.
Okay, so if they come, I'm happy to be interrupted. I will meanwhile keep going.
Okay.
Okay, so let's now motivate the problem of tensor regression. The tensor regression problem is that you have, let's say, a subject and you are measuring some output of that subject, which is scalar valued. So for example, the subject could have some disease and you are measuring whether they have the disease or not. So let's say you are measuring they have ADHD or not. Okay, so the output is just a scalar. In this case of ADHD, it's actually just a binary output, 0 or 1. And what the data you observe is whether they have some disease or not, and you observe some tensor structure data. So in this case, you, let's say, observe their fMRI brain scan, okay, which is 3D. The ideas extend to 3D. I'm motivating it because I can draw 3D cubes better than 4D or 5D objects. So what you observe is that you observe this output Y. You observe what is called this feature tensor or covariates. And the assumption is that this output, for example, whether you have ADHD or not, is some function of your brain scan. So it brain scan because your brain scan is revealing some connectivity within your brain. Now, we will also make the simplified assumption that actually the relationship between the observations and your brain connectivity is linearly dependent upon some unknown parameters. So the idea is that your output is a linear combination of your different voxels in your brain, for example, and that is the unknown. We don't know what that linear combination is. Okay, so this is a notation for inner product. So what I have is Y is the inner product of a tensor with another tensor, which we call regression tensor, or the tensor of parameters, plus some noise, which could be either electrical noise or it could be noise due to a model that you didn't actually, you didn't model this thing well. Okay, So the inner product idea is simply point-to-point multiplication and addition, just like in matrices and in vectors. And now you want to, the whole idea is you want to estimate this unknown B. Okay, people who are more coming from the signal processing background, of course, the unknown is typically written as X. I'm using the statistics notation where the unknown is given by a beta and X is the things that you observe. So if you want to do that, of course, one observation is not going to get you anything. So what you do is you actually have N subjects. So now you collect the same thing for N of them. But still, your N is much, much smaller than the number of unknowns, remember, is P1, P2, P3. You multiply all of them. So the number of observations is still much smaller than P. And your goal is that you want to estimate this P. So mathematically, what we can pose down is that we have observations yi given by inner products between the observed and the unobserved plus noise. Xi is the tensor of predictors. B is the regression parameters, which are unknowns. If you just looked at it blindly, the number of degrees of freedom is P is equal to product of the PKs. And you have observed yi, so everything in green is observed. This is the noise. We want to obtain an estimate of B using these N tuples, both the output and the observations Xi. It is ill-posed, of course, because we have more unknowns than the number of equations or the number of observations. So we can't apply our favorite typical linear algebra tools. We also cannot apply, or we don't want to apply the tools from sparsity or low rank regularization, because even then, for large values of P1, P2, Pk, the solutions won't be satisfactory. So what we want to do is impose additional structure on B to reduce intrinsic degrees of freedom. And the idea is that we assume B to have some sort of a structure. So what we call it is the unknown B is a structured tensor. And there are a lot of works out there that have looked at this problem from different perspectives. For example, from the perspective of a common extension of matrix completion to tensor completion. People have also actually looked at it from the regression perspective, and what they said is, let's impose the structure of what's called a Tucker decomposition. Let's assume that the unknown is a low-rank Tucker, has a low-rank Tucker decomposition. So what does low-rank Tucker decomposition look like? You assume that your unknown is given by a linear combination of rank 1 tensors, and so this is your output B is given by some linear combination of rank 1 tensors, and the number of these rank 1 tensors is not very large. The number of these rank 1 tensors is R1, R2, R3, where R1 is much, much smaller than P1, R2 is much, much smaller than P2, and R3 is much, much smaller than P3. So in Tucker decomposition, rank becomes actually a vector object. Instead of saying you have rank R, it is actually a rank in each direction separately. So so in this case, we'll say the rank of this B tensor is 3 tuple, because it's a 3-dimensional tensor, R1, R2, R3. Okay, so it has 3 sort of sub-ranks, if you want to think of that. And then these rank 1 tensors are given by these what we call the factor matrices, U1, U2, U3. So U1 is P1 by R1, U2 is P1 by R2, and U3 is P3 by R3. So it's kind of like low rank factorization for a matrix, but we have extended that. Another way to think of this is, for example, if you think of it like a 3D Fourier transform, right? What you are saying is that you can think of this G tensor, which is called the core tensor. You can think of these as the Fourier coefficients, and this U1, U2, U3 as the 1-dimensional DFT and or the Fourier transform. And you are saying, well, to get to the final thing, you apply Fourier transform in one direction, then in the other direction, then in the third direction. The only difference is that the coefficients now are not the same dimension as P1, P2, P3. The coefficients have R1, R2, R3. Okay, so I see that there is some kind of a question. There's a question.
Yeah, so the question for everyone is, are the Tucker factors, guessing the terminology here, matrices for K greater than 3? That's from Ryan.
Tucker factors, if I understand the question, I guess you are referring to do these extend to things more than K for K equal to 3 or bigger? If that is the question, that is true. I'm just showing you a 3-dimensional thing, but the same idea extends to 4D, 5D, 6D, whatever D you want. If I got the question right. If not, I'm happy to expand on it.
I think that was it. Yes, so it popped up. I'm asking.
Oh, okay. So yeah, they are matrices. U1, U2, U3, exactly. They are matrices, and that's why they are flat. They are matrices, and the only tensor in here is this core tensor G. Okay, and but you can then went too far. Okay. So the core tensor is the only tensor in the factorization. The only thing that stays as a tensor is the core tensor. The factors are really matrices, regardless of whether they are K greater than 3 or whatnot. What would happen is for K greater than 3, the number of factors is K, okay, but they are matrices. Okay, just like you can talk about K-dimensional DFT, right? K-dimensional DFT uses DFT matrices in each direction, in each dimension, but the DFT matrix stays DFT matrix. It doesn't change. Okay. And here's just a tensor algebra has its own notation. Here's just a small notation. By the way, I should have clarified that whenever I put a bold letter with a underline, that's a tensor. And just a bold capital letter is a matrix. So here's a general notation. This says that you have a tensor G, the core tensor. Then in mode 1, you multiply it with matrix U1. And then you do mod 2, you multiply it with U2. And then in mod 3, you multiply it with U3. And what does it mean, multiply mod 1 with U1 and U2? It's again the same thing. Just think of the higher dimensional DFT, okay? Or 2D DFT, you are first doing the DFT of the columns and then the rows, right? It's exactly the same idea. Okay, so when we look at that, then what happened is, let's assume that you have a low rank Tucker decomposition. What people ended up getting is that the best result that people got was that the number of observations has to be proportional to P max, which is the highest dimension in any one, the highest dimensionality in any one dimension, times R max, which is the highest rank in any one dimension, times capital K, which is the order of the tensor, plus R max raised to the power K log K. Okay, so this is okay, decent, except that if you had, what this is saying is, if you had one dimension which was really large, you are still looking at a very high penalty for N. So while this is imposing some structure and reducing the penalty that you are paying for having a high dimensional object, there's still a large sample complexity that you are dealing with. The other issue with this model is that in many problems, we are interested in imposing sparsity or identifying a parsimonious set of predictors. We want to get a set of predictors that are we are not just interested in reducing the dimensionality. We also want to say, okay, is this the region of the brain where majority of the issues lie, right? Again, I'm giving the example from medical sciences, but this model does not cover that. So What we wanted to work with was we wanted to work with a model of low rank and sparse Tucker decomposition. And we wanted to reduce the the constraint on the number of observations even further, because the problems we were dealing with, the medical imaging problems, had a really small number of observations. So what is the low rank and sparse Tucker model that we considered? It is basically, the idea is the same, that you have a low rank Tucker decomposition, but we also said that the factor matrices themselves, the columns of the factor matrices, are sparse, okay? So the same idea that we have a core tensor, which is very small, R1, R2, R3, which is the rank. And then you have the factor matrices, but in addition to the fact that we say that it's low rank, which means that the tuple is much, much smaller than the original dimensionality, we also have sparsity in the columns of our factor matrices. So this is somewhat like, if you want to think of it like a sparse principal component analysis extended to higher dimensions, right? Where you say that I want to find the principal components, but also want the principal component directions to have sparsity within them. So formally, the definition of a RS, which remember R and S now are tuples, because you have multiple things. They are tuples, they are not scalars. We say that a kth order tensor admits an RS low rank and sparse Tucker decomposition if it has a Tucker decomposition and the dimensionality of our core tensor is much smaller than the dimensionality of our original tensor, and the columns of my factor matrices have sparsity which is much, much smaller than the original sparsity. I want to here also point out actually interesting coincidence that the same time our paper appeared, a similar paper appeared in the same journal actually, which was studying a kind of a similar problem. There are some caveats and some changes. For example, the problem they were studying, they were imposing sparsity in the rows of these factor matrices rather than the columns. And then there are some orthogonality aspects also that are being imposed, but here we are not imposing any orthogonality. Okay.
We had a question come in. Sorry to interrupt. The question from Chawai is, we know that the 2D matrix / tensor has R1 equals R2. Is there any relation among R1, R2, and R3 for the 3D tensor?
So when you say, oh, you mean 2D matrices have R1 equal to R2 because the definition of rank R is just R, right? Like it's not that when you have a 2D matrix, you are not saying, oh, I have a rank R1 and a rank R2. Yeah. So as far as I know, in the higher dimension, there are several relationships that do exist between, you know, there are aspects to R1, R2, R3 in terms of when it comes to identifiability. There's a whole literature in tensor algebra where you talk about when is a, for example, a decomposition identifiable, right? Like, for example, to get a low rank approximation, it's a straightforward thing. You just do SVD, you will get your low rank approximation. For tensors, these decompositions are not always identifiable. So there are some relationships that exist. I'm not fully versed in them, but as far as I know, they're strictly speaking, R1, R2, R3 don't have a very strong relationship between them.
Thank you.
Okay. Okay, so why do we want to impose this low rank and sparse Tucker decomposition? Because it reduces the number of degrees of freedom further than what we had originally. And in addition, if the sparsity is there and the sparsity is large enough, it can also impart sparsity on my original tensor, not the same level of sparsity, but some sparsity. And that can help me at least not maybe identify where all the activity lies, but it can perhaps help me identify the places where there is nothing of interest. Okay. So armed with this, we can pose the problem. We have, again, the same thing. We have observations yi equal to xib. We can now use a compact notation by collecting all of the scalar outputs, for example, disease knows disease, into a vector y. So now I have a n-dimensional vector y that is given by a linear operator which acts on the space of tensor. So this is an operator x which takes a k-dimensional tensor or kth order tensor and maps it to a vector. So this operator is very simply defined as the ith output of this operator is simply the inner product between xi and b. This is just a shorthand notation because I don't want to write write all of these things. I want to use the aspects of linear operators and adjoints. So it helps me write those things in a much more compact fashion than carrying around the whole thing. Okay. So what I want is, the goal is to develop a provably convergent algorithm. Ideally, we want the algorithm to have some sort of a geometric convergence, or in optimization literature, linear convergence. That will help me identify B. And I also want to figure out when is it that I can actually identify B or estimate B using the observations. Here, I do want to clarify one thing which has come up in questions, so I want to clarify here. The goal here is not the way this differs from, for example, some of the decomposition identifiability literature, right? I already said that decompositions are not always uniquely identifiable. Here, we are not actually trying to identify the original decomposition. Our goal is to estimate B, the final thing. Okay, we are not trying to estimate, like, for example, if you are doing if you were doing matrix valued analysis, you would say, I want to understand the singular vector, then you know that the singular vector you can perfectly estimate. Here we are not estimating U1, U2, although in our solution we utilize them, but our guarantees are not on them, because identifiability is a challenging thing when we talk about decomposition. Our guarantees are on the final B, the unknowns. Okay, just wanted to clarify that. Okay, so going forward, the algorithm that we propose is actually a very simple projected gradient descent algorithm. We call it tensor projected gradient descent. So let's take this set B RS tau to be the space of all RS Tucker decomposable tensors, whose core tensor has one norm bounded by some constant. That constant basically just tells me, it's sort of like a bound on the norm of your entire data. It just tells me how much of a bigger space I'm evaluating. It doesn't, from the algorithmic perspective, it doesn't have any significance. So ideally what we are looking for is, we are given the observations Y, and this linear operator, which takes tensors, spits out vectors. This linear operator acts on the space of tensors that only belong to these RS Tucker decomposable tensors. And the formulation is very easy. You say, well, I want to find the best estimate. Okay, so this is the goodness of fit, subject to the fact that the thing that I'm fitting, the tensor I'm recovering, must lie in the space of RS Tucker decomposable things, right? So this is like, pretty much any other regularization-based method that you look at. Of course, the key is how do you actually solve it. In our case, instead of posing a regularizer and making it an unconstrained problem, like, let's say, lasso for sparsity, where you get rid of the constraint of sparsity and just plug in the constraint, we do more sort of like say iterative hard thresholding kind of an approach, right? Which is also a projected gradient method for people who are familiar with the compressed sensing literature. So the TPGD algorithm, it has actually, very simple thing, connections to IHT or iterative hard thresholding. It basically has a gradient descent step. So you can find the gradient of that. That is simply given by the conjugate, your adjoint operator. And then you have the original operator times your previous estimate minus your observation y. So this is your gradient. This is your prior estimate. Your next estimate is simply prior estimate minus a step in the direction of your negative gradient. I already said minus. So your previous estimate and a step in the direction of your negative gradient, right? This is just so. So this is your gradient descent step. But of course, this step will probably take you out of the space of RS sparse and low rank Tucker matrices. So now the next step is projection, right? So you do a simple projection step, you take your estimate and you project it onto the space. And now the question is, how do you do that? That's where the challenge lies. In fact, doing this is kind of an NP hard thing, but we can actually, as I said, this step is very much similar to a sparse PCA kind of a step. So what we can do is, how do we solve the projection step? Actually, we don't need to. There is something in the literature that has been proposed called sparse higher order SVD, which is that you take a tensor, you give it the rank tuple and the sparsity tuple, and then you you matricize your tensor in each mod, right? So mod K matricization is simply taking the stacking the mod K fibers of W or your tensor into a matrix. So you take your tensor, for example, if it's 3D, you take the slices back and you keep on putting them side by side, right? So that's mod 1 tensorization, matricization. So now you are left with matrix. So if you have kth order tensor, you have K of these matrices. So what you do is, for each matrix that you get by matricizing the tensor, you find its sparse PCA, rank R SK sparse PCA. And you use those as your factor matrices. And once you get that, you then use your original tensor, you project that to get your core tensor. So a very simple algorithm. And this kind of covers the direction of what is the algorithm that you want to use this projected gradient descent using this sparse PCA approach. You matricize in each dimension and you do sparse PCA, that's it. Okay, so the question is, how well does it do? To do the convergence, we have to use a similar idea that is used in many of these works, which is that, well, you are dealing with an ill-posed problem. You have more unknowns than the number of equations. So you better make sure that the problem, at least you can only solve the problem when you restrict yourself to the class of unknowns you are focusing on. At least the problem is solvable in that case. In particular, we know that none of the things that you are interested in none of the things must lie in the null space of your operator. Okay, so this is a classical idea has been used in sparse regression, in compressed sensing, where it's called restricted isometry property. So we kind of use the same thing. We say that the linear map that we are after, which this map now takes tensors, the map does not, when it acts on tensors that belong to rank R and sparsity S tensors, it does not send it to 0 and it does not inflate it too much. Okay, so it kind of keep things close. Now, dealing with this RIP property is a little bit more challenging there because, for example, you have to show that, well, if you add two RS sparse low rank tensors, what is the end thing, right? It is not as simple as you add two S sparse things and it is 2S, but the result ends up being the same. So there are a little bit more challenges involved in dealing with this kind of an RIP, but at the end of the day, what we get is a very nice convergence guarantee for our tensor projected gradient descent method, assuming that the projection step is perfect. And that's the caveat here, that the projection step has to be assumed to be perfect. And the method we are using in our algorithms is that sparse PCA, but someone may have a better projection step and may get better results. So let's break this theorem down. So what is the theorem saying? The theorem is saying that assuming that the original tensor belongs to this low rank sparse tensor world, and your map, your linear map satisfies this Tucker-based RIP, then fixing a constant step size, using a constant step size for your projected gradient descent, what you get is that the error between your estimate at step T and your original unknown parameters has a geometric decay or linear convergence, which is multiplied by your initial error, your initialization error B0. And the estimation error is proportional to the noise power, the noise that you had. Okay, in particular, if the noise was 0, then this thing will converge exactly to the right solution at a geometric rate. Okay, so this is all well and good, but the question is, I haven't told you how many observations do I need, and to get to the observations, I need to actually look at a specific map. In particular, I need to find out, are there linear maps that take tensors and make sure that the energy is preserved? So to do that, we focus on sub-Gaussian maps. A sub-Gaussian map is simply a map in which each of the covariate is assumed to be a sub-Gaussian random variable. A sub-Gaussian random variable is actually not a random variable per se, but it's a class of random variables. So a sub-Gaussian random variable is any random variable whose tail is dominated by a Gaussian distribution. The example is Gaussian, bounded, uniform, binary. All of these are sub-Gaussian random variables. And what we are saying is that if the tensor X's, that observations that you had, if the entries of them were independently drawn from these sub-Gaussian random variables, so they don't need to be identical. One entry could be Gaussian, the other could be uniform, the other could be binary, but they all have to be sub-Gaussian and independent. If you do that, then it turns out that you will satisfy the RIP with n greater than or equal to, you have summation of SK RK plus the product of RKs. Now remember, this product of RKs is the number of unknowns in your core tensor. SK times RK is the number of unknowns in your kth factor matrix. And so the summation is the total number of unknowns in all of your factor matrices. And so, and there's a log factor. So if we compare our result, and for ease purposes, I am just saying, let's assume that all the dimensions are equal. P1 equal to P2 equal to Pk. All the ranks are equal, R1 equal to R2 equal to R bar. And all the sparsity levels are equal. So here are some relevant works that we can compare with. So these two works, of course, had very high penalty. Like this one had P raised to the power K, very bad. This one had P raised to the power K by 2. This one did not have P raised to the power K, but it was R times P. And if P is large, R times P times K, if P is large, this can be pretty big. And what we have done is that we can get rid of this P factor and replace it by S factor. And S is much smaller than this P, okay? In particular, you can do the analysis and figure out, for example, the data sets that we were working with, P bar was 128 and R bar was 3 and S bar was 10. So if we applied the number of observations here versus the number of observations that we got, the difference in the number of observations or the number of subjects you need is an order of magnitude. Okay, so the huge savings. Okay. So, again, I'm going to point out to this work that appeared simultaneously with our work in the same journal, which is also which has minimax guarantees, and they actually show that this is the best that you can do with any method. So, in the interest of time, since I'm kind of running behind, I'm going to skip this synthetic data experiment. This just shows that we do pretty well compared to other works. And in fact, if we do these violin plots, our method actually has a much better concentration than other methods. I'm going to jump to the real data set, which is called the ADHD 200 Consortium. It is meant to study ADHD using fMRI data. There are 8 international imaging sites involved in it, but we are dealing with, we use the data from 3. I guess there is a question.
Yes, yeah, the question is from Chawai. He says this question is a bit numerical in flavor. Since the problem of tensor decomposition has the whole data set given, is it beneficial to let the step size be adaptive?
So the adaptive step size only makes sense if you, if you are basically, if you can't get convergence in, if you can't get convergence guarantee for a static step size, right? The best results, of course, you want the step size to be, the classical rule of thumb for optimization, right? You don't want the step size to be, you want the step size to be large enough, but not large that it will start diverging. So the constant step size is actually what in gradient descent, you want to work with a fixed step size. I'm not sure if adaptive step size will gain you anything. In fact, it will only, like if you, for example, the rule of thumb is that if you can't get it with a fixed step size, then especially in stochastic optimization or stochastic approximation, you decay your step size, but that's going to actually slow down your convergence. So the better thing is to actually work with a fixed step size. I have another question, I guess.
Yeah, from Dror, he says, at a philosophical level, you seem to be saying, let's use the residual or unexplained part of the measurements to adjust our estimate. For example, using some gradient descent style, in parentheses, treating the residual as a gradient. Many have studied how to use this gradient information in a statistically meaningful way. Is this a fair way to interpret your approach?
So that's a very good question in the sense that, once we pose our estimation problem, there are different lenses that we can look at it and try to get to what we are trying to do. The lens that we looked at was purely from an optimization perspective. We said, well, now we have reduced it down to an optimization problem. And let's, this optimization problem has, of course, some, local minima and some global minima. Let's see that if there is, the optimization problem is non-convex, but let's see under some constraints, can we find the global, can we find the right solution, which may be local or something, but we are getting to the right one. So we looked at it completely from the perspective of just the optimization landscape, right? So this is the optimization problem under these constraints. does the gradient descent solution, which is going to converge to a stationary point. We know it is our analysis shows it's going to converge to a stationary point, but does the stationary point happen to be the right thing? You can now view the gradient descent step or within that, and from a statistical perspective, and try to interpret it in a different way. We have not done that. We have completely just looked at it from the optimization lens. So I need some guidance here in the sense that I think, according to my clock, it's already 11. So, you know, I mean, the kind of upshot I have is that we do some experiments with real data set where there's a huge disparity between the number of observations you have and the number of unknowns you have. So for example, the number of unknowns without the structure is 133,000, but the subjects is only 305. So huge disparity, and we don't claim to do very well, but we do seem to be doing much better than, for example, something like support vector regression or lasso or the prior methods. Okay. So I think, you know, in the interest of time, I probably don't have time to go into dictionary learning, which is a flip side of this, which is how you use tensor data. How do you do feature learning or tensor data in a similar manner? And in this case, actually, we also have minimax optimal results. But I presume I don't have time. I'm going to seek guidance from our hosts, and I can, you know, I probably should summarize. But Spiros, can I have some guidance, please?
Yeah, I mean, maybe I see we still have a few people on, so I think there's probably a little bit of flexibility schedule-wise. Maybe we could spend another couple of minutes, 2-3 minutes on it or something, just to let people hear what you've been working on in this area.
Okay, sure. So you know, dictionary learning is a problem that's a feature learning problem that helps you learn features which are in between sort of linear component and linear principal component analysis, which is a linear feature learning method, and kernel-based methods, which is a non-linear feature learning methods. And so the idea is that you are given some data Y, and you are trying to basically you are trying to learn a map that takes it to this domain M-dimensional space, where the features are sparse. Okay, and so the main thing here is how do you learn this map MD, which is simply given by what's called the sparse coding procedure. And to learn this map, what you need to know is a dictionary D, which is a large collection of vectors. So it's this D now is a very fat and short matrix with unit norm columns, and you are trying to find the D such that your data is pretty much is well represented in D using only sparse coefficients. Okay, so now X is the unknown, X is my sparsity, and D is also unknown. And so, stating it differently, what you are trying to find out is you are trying to write your data Y in terms of an approximation D times a vector X, where X is sparse, and you don't know either one of these things. So this is a factorization problem. And of course, to solve that problem, you need more than one data sample. So what you have now is N data samples, the same. The dimensionality of each sample is M, and you are trying to learn a dictionary which is M by P. So P is again very large, okay? And this matrix X is unknown, which is P by N. So dictionary learning is an old problem, has been solved in a number of ways, but our goal is, and here are some of the references that you can look up. The main lesson from dictionary learning is, and this started appearing only recently, is previously dictionary learning started by proposing some algorithms. And then people looked at and asked, okay, what's the number of measurements you need to recover the D? And what they learned is that these are sort of the bounds. These are that N, they said that you cannot learn a dictionary if the number of measurements is any smaller than M times P squared times this epsilon factor, which is the error in the dictionary you're learning. And people proposed a method. So this is like this is the achievability bound, MP cubed, and MP squared is the impossibility bound. So anything smaller than MP squared observations, you would not estimate. You are guaranteed to not estimate anything meaningful. And with MP cubed, people showed that you can. So there's a gap between the upper bound and the lower bound. But regardless, you see that for tensor data, so if this Y was now tensor valued, okay, which means that your dictionary is also tensor valued, P is huge, M can be huge also. And so what you end up with is the requirement on the number of observations can be huge for learning the features. So we want to do the same thing. We say, well, dictionary learning for tensor data is you have a k-dimensional tensor data. You are trying to learn features for now this tensor data. So think of it as a video, for example. And instead of learning a dictionary by basically vectorizing this data, so you are not going to take this YJ, vectorize it, because then M will become huge. And so in dictionary, P is always bigger than M, so P will become huge. And now you are looking at MP squared number of observations, which is very large. So instead of that, we do the same thing. We say, let's assume that we have a sparse Tucker decomposition, but now we are in this dictionary learning realm. So my core tensor is now bigger. Instead of smaller, it's bigger. And it is also, my core tensor is now sparse, okay? So what I end up with is I have these factor matrices, which I now call single mod dictionary. So D1, D2, D3. And the whole point of that is if I do that, it turns out that if I impose this structure, you can now vectorize it. And I'll get to the kicker and then I'll leave at that. Now, if I vectorize my data, what I'm saying is that actually my dictionary should be a canonical product of smaller dictionaries. So my dictionary learning problem now reduces down to learning a dictionary. I can now vectorize my data, but my problem now reduces down to learning a dictionary that is given by canonical product of smaller dictionaries. So let me just show it a pictorial representation, and that will be pretty useful. So let's take the example of a square dictionary. So I am trying to learn a dictionary for images which are 512 by 512. So M1 by M2 is 512 by 512. And let's assume that I want P to be equal to M, square dictionaries, right? So if I vectorize it, I get M equal to 2 to the 18. And so if I do P equal to M, then the total number of parameters that I need to estimate are 2 to the 36, or 6,871 billion parameters. Now, of course, this is meant to exaggerate, but you get the idea, right? That if I take this whole image and I vectorized it and didn't impose any structure, I have about 6,800 billion unknowns. And if I use the requirement that N should be MP squared, well, good luck finding that many samples to learn the dictionary. On the other hand, I can say, well, I actually am going to require that my dictionary is a canonical product of two smaller dictionaries, and each of the dictionary has size M1 by P1 and M2 by P2. Okay. If I do that, then I only end up with 524,000 parameters. And you can look at the difference between the numbers here, about 7,000 billion parameters versus 500,000 parameters. Orders of magnitude difference. And basically by doing this, we make the problem well posed because we need very fewer number of observations to learn the dictionary. So the rest of the talk is basically based upon showing results that actually indeed we can do that, and also deriving minimax lower bounds and upper bounds, and you showing further results. As I said, we have a Cambridge University book came out, which has a chapter from us on this, which summarizes these results. In the interest of time, I mean, here are some results comparing with, this is another kind of a interesting result that might interest some people, which is, we then also proposed a new model, and the effect of that was that to learn a dictionary using KSVD, KSVD required, had the number of parameters, 147,000 parameters. And we got the same performance as KSVD using only 265 parameters. And if you are trying to save these things in, for example, a mobile phone, you are using only 0.18% of KSVD, which is a popular dictionary learning method. So with this, I'll stop here. There are publications that can be seen on the website. I'm happy to answer more questions, but I don't want to keep people here longer than they have to. So I'll conclude here and happy to take questions.
Thank you very much for the presentation. That was great.
Thank you.
Are there any questions? I know there was one question that came in about the recording of the presentation, and that will be made available on our website. I think we may have time for one question if there's anything else from the audience. With Zoom, we have to wait for the typing delay as well.
Yes.
Don't see any yet. There's no way to know if someone's actively typing, so I'm not sure.
I'm happy to, I mean, if something comes up in people's mind, I know I had to rush the last part especially, but I guess the compromise was I could cover the first part in detail.
So thank you very much. It was very interesting to see the full breadth of what you've been working on. Yeah. Well, I don't see any other questions that have come in, so I think we can probably end here. I will make the recording available, as I said, and I think the audience, if you have any other follow-up questions, you're more than welcome to reach out to our speaker via email. And I know that a couple of our faculty are planning on also catching up with you separately, which will be another opportunity to talk, I'm sure. So. Yeah, with that, I want to thank you very much again for coming and joining us today and for giving this great presentation. We really appreciate the time.
Thank you so much, everyone. I really enjoyed the virtual visit, which will continue in pieces.
We do it in the fragmented way that we can, optimization.
Absolutely.
All right. Well, thank you very much, everyone, for attending today, and have a great weekend as well.
Have a great weekend, everyone. Thank you.
Goodbye.